Hello everyone, I'm Tieyuan Zhu from Penn State. Thank you all stayed so late to attend my presentation. It's also my honor to kick off the section. So today I'm going to talk about how we're going to train the deep learning model using limited seismic data. I hope you found my presentation being interesting because there's huge potential to using the deep learning for the long-term monitor problems in geophysics. All the technical work was done by my recent PhD graduate Z. The research question we're dealing with are how can we train the reliable deep learning models in cases when the field data is limited? How can we evaluate our results? And can deep learning provide some new knowledge to the problem? First, to bring all of us to a same page, I want to start with a classic machine learning problem. So if you want to identify objects from a massive imaging, so what you do here is you prepare all this image with objects, without objects, with labels. So for example, here you tell is it apple or not apple, and then you train the neural network. After you training, you can input the new image with object or without objects, ask for prediction. So what I want to emphasize here is we need a large data as well as labels for each data set. So that's a preconditions for the successful training procedure. So this concept has been very successful applied to some of geophysics problems. For example, earthquake phase detection. So you can feed the seismograms and labels to neural network to train the model, and then you can predict the phase. So this has been very, very successful in our field. However, in some of our geophysics research area, we don't have much field data set available for this training set. I borrow this picture from Mosavi and Broza's paper to convince you this is the case. So the author tried to summarize a number of papers in different research areas with training data set size. As you can see, in the right-hand side, labeled as a field data, in the left side with synthetic data. If I summarize this for you, in the right-hand side, if you're dealing with signal classification, pattern identification, so you tend to have many field data for your training exercise. But if you're dealing with a subsurface property estimation or imaging, you tend to have many synthetic data. You don't have field data set. So here, if I list the two challenges we are facing now is we actually lack a sufficient training data set, especially in subsurface geophysics research. At the same time, we lack of labels because we don't know much subsurface properties. So how we deal with this problem in the past? If I formulate my problem as y equal to fx, so when you have a limited observation, so you want to estimate a unknown model, subsurface model, for example. So we have to rely on the physical law we studied in past decades. And then we can add a regularization in the inverse problem, for example, smoothing, to get a reasonable solution. In a similar way, if I write a machine learning as a y equal to fx as well, so we have to rely on the large input data and labels to train the neural network very well, and then to learn the f, because we will assume we don't know the f here. But when we have a limited data, even we don't know the labels, so this creates a situation we just cannot perform the training very well. So here we propose a solution to use a forward modeling to generate the data from the synthetic models. So we know the physical law very well. For example, for seismic propagation, we know the wave equation, right? So assumption here is our physics law is able to describe our data very well. And then if we feed this rich data set to the machine learning with the labels, so we actually have a good chance to learn the unknown f function. So here, as you can see, we can generate the data as many as we want. So this essentially, we can train the neural network very well. In the following slide, I'm going to show examples to walk you through to demonstrate how it works for field data set. So the first example is from the Frio CO2 sequestration site from West Texas. So the situation we face here is after we inject the CO2 plume in the deep reservoir, we want to use a seismic method to track the CO2 plume migration. But in the practice, we only have one source in the left and then 13 receivers in the right. So we are unable to track based on the conventional inversion problem. If you are familiar with the seismic migration or tomography, you're going to quickly realize we actually lack of the rig coverage, so we cannot perform the tomography task here. So I'm going to show you next is how can we use a deep learning to overcome this difficulty. As I mentioned earlier, because we have limited time-lapse seismic data for the training, so we have to build a synthetic data to train our neural network. So here I'm showing you a workflow to generate this training data set. So first, we have to build a good background geology model. So that means we need a very good PV velocity model, for example. And then, because we are dealing with CO2 plume, so we need a reservoir simulation to help us to simulate how the CO2 migrates through the reservoir. And then we have to convert this model to seismic property models using rock physics modeling. And then we can generate seismic data using forward modeling. So with the seismic data gather and the CO2 plume, we can train the neural network. Here I name as a seismic CO2 net. So let's look at closer look at seismic CO2 net. As you can see, this is the basic UNet setup. So what we input is seismic gather and a CO2 saturation map. And then we throw the several convolutional layer to learn the information between these two. So in the first step, we need to build a good background model. So we can build, for example, for this case, we can build a PV velocity from sonic log, and then porosity map from the porosity log. And then we need to do some reservoir random simulation to build this 2D map, permeability and porosity. So with the porosity, so we can simulate the different CO2 scenarios. As you can see, I'm showing two cases. Because of different permeability, you can see the CO2 plume migrate with a different speed and also different shape. So with actually thousands of these realizations, and then we build CO2 saturation maps. With 1,000 CO2 saturation maps, we can convert it to a PV velocity map and a seismic attenuation model using Gaussian fluid substitution. Finally, using PV velocity model and attenuation, we can generate seismic data showing at the bottom. We are basically ready for training. So we input a seismic gather and a CO2 saturation map. As you can see, some examples in these slides at a different time lapse. So the first exercise is validated with some synthetic data plus noise. This is not surprising. You can see my prediction CO2 saturation plume is pretty much close to the ground truth, just with some deviations. The data match is also pretty good. Now let's look at the field data, how our trained model performed with the field data. At the beginning, I feel this is a very challenging task is because the complexity of field data. There are lots of noise, there are lots of reflections, codas, nonlinear amplified effects, but our synthetic data mostly missing all these elements. So how does that be? But finally, as you can see, I'm showing the results here. We actually recover the CO2 plume very well. And then how are we gonna evaluate our results? So we basically compare our results with physics-based simulation results using software TOF2. As you can see, the most CO2 plume can be recovered overall. But some details are missing. This is actually because the limitation of our GPU memory, so we actually decimate our model to a smaller size and then interpolate our model back to this size. Please keep in mind we only have one source here. This is impossible task for conventional seismic inverse problem to image CO2 plume. Deep learning training model train on the synthetic data and then apply to the field data to provide us some information about CO2 plume. This is definitely something is better than nothing. If we want to further evaluate our results, we compare the data matching from the predict model and also the field data. As you can see, if you only look at the first level, they actually match very good. I think I'm satisfied with that, but the amplitude is definitely off. Again, I hope I can convince you this technology is useful for the time-lapse seismic monitor for the CO2 problem. My second example come from Newberry EGS site. So the goal is to locate micro-earthquakes. So we only have 8 stations on the surface, and then we have about 400 events in total during 2 simulations. So again, this is not enough for our neural network training. So what we did here is to build a nice geology model from some tomography results, as you can see in the left. And then we synthetic the micro-earthquake location everywhere in our models as a purple color here. The green dots and the blue dots represent the catalog micro-earthquake location. So we try to cover the big area as we can to simulate all these scenarios. As you can see some number at the bottom, so that's not important for us now. And again, first the exercise is a synthetic test. So as you can see, our prediction is quite close to the ground truth. So the error is about 50-80 meters. So that's a pretty satisfied results. But important information I want to give to you is our prediction is very fast. Just take a few seconds. Next, let's look at the results from the field data set. As you can see here, we predict all these green dots above the stimulation zone. Stimulation zone is about 2 to 3 kilometers. So we ask a question, what happened here? And then we go to the previous results from the physics-based prediction. We can see some consistent about the source distribution. So the reason actually is because of casing leakage. So that's why the micro-earthquake propagated above the stimulation zone. And then next, we apply this trained model to 2014 field data set. So with this data set, we have some new discovery. In the stimulation zone, you can see there are some consistency of the source location. But below the stimulation zone, so we predict a much less source micro-earthquake compared to the physics-based prediction. And then if we compare to our results with a natural fracture study, we can see natural fracture actually mostly stay with the stimulation zone. There are very few below the stimulation zone. So we think our results is better match with the natural fracture distribution. With that, I want to conclude my talk. Let's go back look at the 3 questions. So how can we train the deep learning model? So we can use the physics-based simulated data to train the neural network. We can use the data match to evaluate our results. And we think deep learning can bring some new knowledge. For example, in our CO2 example, with only one source, we cannot perform any conventional inversion. But the deep learning provides us a way to overcome that difficulty. And also for the micro-earthquake, we think we provide some results better match with the natural fracture study. One last selling point I want to say is first, the prediction is very appealing for monitor problem. Thank you very much. I would like to take questions.